Good evening, everyone. Welcome to the inaugural lecture for the San Luis Obispo Sustainability Group Award for Energy and Environment. It's also a Hearst lecture, so we're doing kind of a hybrid here, if you will. The purpose of the San Luis Obispo Sustainability Group Award for Energy and Environment is to recognize an individual or a team who has advanced the state of the art in design, analysis, related tools for improving energy performance in the built environment, including work that's characterized as green, sustainable, resilient, and zero net energy. So Ed, you'll appreciate here we call it tech fun, or building fun, or tech, so we keep the fun in there. So those that are selected for this award will have advanced the field of sustainable design through any of the following means: built projects, design tools, authored books or articles, or any other high-impact teaching, research, service, or creative activities that are related to this. In our inaugural award, we picked someone that has done all of the above. He's contributed in every arena, so really a significant figure. So this evening's recipient covered all of the above, but first just a couple of words of background on the award. The award has been named for the solar and sustainable design firm, San Luis Obispo Sustainability Group, which was formed by the passive solar architects and Cal Poly architecture professors emeriti Ken Haggard and Polly Cooper. If they could wave. And so Ken and Polly, together with another professor emeritus, Phil Niles from Mechanical Engineering, wrote the California Solar Handbook in 1980, and that was done for the California Energy Commission. This book, together with early computer simulation software, CalPass, written by Phil Niles, provided the basis for future generations of designers, architects, builders, and engineers seeking climate-appropriate, energy-efficient, thermally comfortable, passive solar design solutions. So we've been doing this a long time, and it's time to step it up. I mean, this is it. We'd also like to acknowledge in the introductions that the award was made possible by a generous founding gift from the Cal Poly physics professor emeritus, Dave Hafmeister, and his wife, Gina. Dave and Gina? Thank you very much. So in addition, we have high confidence in this gift, and so there was also a Cal Poly College of Science and Math alumni who's an inventor that was working in the field of infrared technology. So you know those really cool ray guns that you can use to measure surface temperature? So this fellow invented this type of technology. His name was Jim Woolaway, and so James contributed also to this endeavor and to a tool shed that we're building in the NRC, which you might have seen the very beginnings of that. So with that, I'd like to introduce Sandy Stannard. Professor Sandy Stannard will do an introduction of our esteemed award recipient.
Thank you. I'm Sandy Stannard. I teach in fifth year design, and I teach in the technology coursework. So some of you have seen me, and some of you will see me, and some of you have seen way too much of me. It is my incredible honor to be introducing our guest this evening, Ed Mazria, our award winner. We're absolutely thrilled that he's our inaugural award winner. This is a great way to start this program. So, it's the architecture, stupid. This was the message that Ed Mazria sent to the architecture community in 2003 in this journal right here. It was a short magazine article that served as an awakening for the architecture community of the essential responsibility borne by the architecture sector in relation to the environment. It was here that Ed delivered the fundamental message that architecture, with all of its material flows and energy involved, consumes 50% of the US energy pie. Ed has been dedicated to environmentally conscious and responsible architecture throughout his career. We can see this, and you will see this, through his own design work and through his authorship of an early design handbook, the Passive Solar Energy Book, great resource. who some of our esteemed emeritus faculty also participated in. This is a seminal how-to book for a responsive solar design. But in 2003, at the time he wrote the article, it was as if he was sending a message to himself. It's the architecture, stupid. And he responded. At this point, Architecture 2030 was born. For those of you who may not be familiar with Architecture 2030, and I'm not entirely sure how you've escaped that knowledge if you haven't got it yet, Architecture 2030 is a nonprofit organization dedicated to responding to climate change. From the outset, Architecture 2030 delivered straightforward, easily comprehensible energy targets to the design communities. And since that time, Architecture's 2030's mission and message has picked up both momentum and magnitude. Through Architecture 2030, Ed has used his significant reputation and communication skills for defining paths toward reduced energy consumption and carbon neutrality in the built environment. The 2050 imperative, the 2030 challenge, the 2030 palette, the zero code, some of which he will discuss this evening, all are conceived to help the design communities reach carbon neutral and zero net energy goals. Realizing that speaking to his own community was not enough, Ed has engaged civic and government leaders from the micro-local to the macro-global to help leaders, decision makers, and code writers help us all achieve zero net energy goals. It's the architecture, stupid. This message continues to resonate. Ed's example demonstrates that achieving zero carbon through design and planning is an achievable goal. Now he's going to tell us about the next built environment today. Please join me in welcoming our award winner, Ed Mazria.
Can you hear? Is this on now? Yep, good. I can see the book is really well worn. The pages are falling out. It's got tabs in it. That's good. It's still going today. I'm going to talk about that a little bit. But so we're going to have a little bit of fun on this also. We're going to talk about where we were, where we are now, and where we need to go. So this is where I started my architecture career in 1958 at Pratt Institute. That's Higgins Hall. And the first week, I didn't know anything about architecture. We had a guest lecturer the first week, and the guest lecturer was Louis Kahn. So I was a week into school, and Louis Kahn came to speak. Now, I asked Sandy and Margot to ask a few of you students to bring a pad and 2 pens. So if you have a pad and 2 pens, open the pad and get ready with the 2 pens. So Louis Kahn, they introduced Louis Kahn, kind of like they introduced me, but Louis Kahn was a very special guy. Small, white hair, always a black suit, white shirt, black tie. They introduced him. He walked in. He was a legend. He walked in. And at that time, there were no projectors, no screens, no computers, no nothing. There was a blackboard and a piece of wood on the bottom of the blackboard with an eraser and chalk. So Louis Kahn walked in and didn't look at us. And he walked over to the blackboard, and he looked up at the blackboard, picked up 2 pieces of chalk, 1 in each hand, right? And without looking at us, he started to draw simultaneously with each hand, and this is what he drew, right? So this is what he drew. And you can try this as I'm playing this. So he started drawing lines with one hand and this other thing with kind of a star with the other hand at the same time. So see if you can do that. But it's got to be simultaneous now. You can't stop. You just do one and the other. And then, when he finished that, he started to write words. This 2 different words. Let me step over here. 2 different words simultaneously. So silence and light, right? And he wrote those 2 words. And then He went back up and he connected the lines on one side, which was silence, to the drawing on the other side, which was light. And he was still not facing us. He was still looking at the blackboard. And we were like mesmerized. So we all took our pads out and give me a pencil, give me a piece of paper. We were all trying to do this. No one can do it. So has anybody done this? And no? Hold up. Somebody did it? It's nearly impossible. We don't know how this guy did it, but he did this, right? And now he's standing there with silence and light, and he says, now again, without looking at us, he says, silence to light. At the threshold of this crossing is design, and he writes design up. And he says, design is a calling on nature. And we're all like, freshmen, 1 week into trying to learn about architecture. And he says, design consists of space, time, and the environment. And he writes that up there. And then he turns back to us and he starts his lecture and shows us buildings and all that kind of stuff. Well, so what's happened since that time, since I started, like you all, as a freshman, like many of you as a freshman in architecture? Well, fossil fuels became prevalent and kind of interrupted the silence and the light, and essentially it eliminated time in the environment, and we were left as architects with space and form. So since that time, we could then control any environment. We didn't have to relate to the exterior, the natural environment in an interactive way. We could look at it through glass and things like that, but we didn't have to. In fact, the wisdom at that time, the engineering wisdom and architecture wisdom at that time, was to keep it out so that the mechanical systems would work and so you wouldn't screw things up, and you could keep 70 degrees day and night and light the environment the same light level, didn't go up and down, no clouds passing by. So that was the conventional wisdom for years. So now let's go back before that time and see what architecture was like. This is Marrakesh, 31 degrees north latitude, so it's south. It's hot and dry. And if you look, this is an aerial view of the old part of the city, so the pre-industrial part of the city, before the Industrial Revolution. And you can see every building is a donut. Every building is a square donut, and they're all compacted together like a bunch of cells. And if you try to find the street, it's almost impossible to find the street. So this is what the building form was like. And the reason it was like that, because they didn't have electric lighting or electricity, and you had to light all the spaces during the day so you can see where you're going and everything else. So you had a donut with a very thin floor plate, but you wanted a big space, and you wanted to live indoors and outdoors. You wanted enough space. And so they formed courtyards. So they lit the space from both sides. They formed a courtyard. They planted the courtyard so the sun wouldn't come in, and the trees would then catch the sun, and the courtyards would stay cool because the cold night air would drop in the courtyards, and then if you kept the sun out, you'd have cool surfaces all day. So that's what it was like in Marrakesh. So indoor, outdoor, you lived indoor and outdoor, and everything was daylit. And if you try to find a street, here's this main street. That's a main street. The streets were really narrow. The buildings were 2 stories, 3 stories tall. Why? And it was all masonry. Everything was masonry. Why? Because at night, the air was cool, would drop down between the streets and everything, cool off all the masonry. And because the streets were so narrow, no sun got in. So you could walk around the streets all day, and it was somewhat, so no air conditioning, no electricity. Architecture worked. Architecture and planning worked. If we go up to 46 degrees north latitude, Vienna, cold, snowy, everything else, what do we see? We see donuts. Again, all the buildings are donuts, and they're all packed in together. And the reason is they didn't have electricity up there either. And they had to light all the spaces. And so they had to light it from both sides, and they created courtyards to do that. But now, all of a sudden, the streets are. Why? Because it snows and you want to get sun in there to melt the snow, and it's cold and you want to be able to walk in the sun. So this is what a pre-industrial building looked like at that time. Masonry, high windows, high floor to floor, so that you could throw light in, a courtyard so you can get light in from both sides so you can light all the spaces. Windows were operable so you can get cross ventilation, and it worked. Okay, now fast forward to 1891, about the time of the Industrial Revolution. Keep your eye on the Flatiron Building. That's this tall building with a spire there, right? So that's Toronto, 1891. That's a 4-story building with a little attic. And the buildings to the right are 3-story buildings, 3- and 4-story buildings, but 3-story buildings, about the same height. So there's a person over there, about 6 feet tall. So floor to floor was what? 18 feet, 15 feet, 20 feet, floor to floor? So that you could throw light in as far in as you can get it. The higher the window, the deeper penetration of light for daylighting. Again, electricity was just coming in at that time. So these buildings were built before the electricity came in. So 1891, keep your eye on the Flatiron Building. I'm going to fast forward from 1891 to 2010. So, look at the Flatiron Building, 4 stories. Now look at the brick building to the right of the Flatiron Building. That is a 9-story building. And look at how deep the wall is with no windows on that side. So now we can climate control the space, we can light space, we can do anything we want. We didn't need the donut shape anymore. We moved away from that into horizontal windows, lower floor to floor. We packed in space, and we can climate control everything because fossil fuels at that time didn't cost anything. It was relatively cheap. Okay, so how did we get there from the Flatiron Building to 2010? Well, it starts with the Industrial Revolution. At the start of the Industrial Revolution, the industry needed workers, and there weren't enough workers to go around. Everybody was fighting for a job, so wages were really low. All the workers were packed in to the industrial area. There was no zoning at that time or anything like that. Everything was based on coal, so you had slums in where the workers were packed in 10 to a room, 8 to a room, 3 families shared 1 apartment, things like that. In New York, where the Industrial Revolution began to spread. So things were really bad. And in fact, if you look at some of the drawings at the time, the factories were belching out coal. You couldn't even see the brick. All these buildings were built out of brick, but there was black soot on you couldn't see the brick on the walls. Conditions were miserable for people. So what happened at the time? The architecture and planning community said we had enough. This is not what we do. We're supposed to make the world a better place, all this kind of stuff. So they had the first international congress, and they called it modern architecture. And that was back in 1928, right when the Industrial Revolution was at its kind of heyday. And the architects met in 1928, and they set out guiding principles for social justice and reform. Basically, to start a revolution, an architecture revolution, and get the housing, get people decent housing, get sun in, get rid of the cold areas, move the housing out of the coal areas. And so they set out, the architects and planners set out a set of revolutionary principles. They call for function-based zones, get the housing out. Put the housing in the best land and the industry in the worst land with all the coal and the dust and everything else. You get high-rise housing blocks so you can get sunlight into the housing blocks. Face them south, put them in land. solar exposure for all spaces, so everybody had sunlight. And they called for free and efficient circulation. Then streets were teeny, and you couldn't get cars through it, and the automobile came in at that time, and they were transporting goods and services and things like that. They wanted wide boulevards. So they laid all that out. Le Corbusier, one of the founders of the international movement, laid out the 5 points toward a new architecture. How are we going to develop now the buildings? Well, we wanted a column wall separation. Because you had to bring the loads down, and the windows were very narrow because you had to bring the loads down high floor to floor to bring the light in. Now you could squeeze that down and use columns inside and then hang the wall on so you can open the wall up. So they want to get as much light in as possible. So we call for a column wall separation, free design of the facade. Once you hung the facade on, it was structural, you can do anything you want and open it up. Call for big horizontal windows so we could see out. And free design of the plan. The columns let you then put walls wherever you wanted, and not just teeny rooms. Now we bring space up. And what was interesting was he called for any space you took, any place you took parkland out, you'd put it back up on the roof. So we didn't lose any park space. So those were his points toward a new architecture. And then in 1925, we have what's known as pretty much the first. There were a bunch of modern buildings, but this is considered the first contemporary building of modern architecture, the Bauhaus. And you can see that the wall is now hung from the structure, columns move inside, big light and airy space, and we can now climate control that space by running hot water baseboard heating along the windows. Those had all single glazing back then, and then we can climate control and light because we have electricity, light all that space. So this was how modern architecture started, as a revolutionary movement for better conditions during the industrial times and industrial revolution. In 32, the movement kind of got corrupted in a sense. And there was a big exhibit at the Museum of Modern Art put together by Henry Russell Hitchcock and Philip Johnson called the International Style. Given now that we can climate control any space, anywhere, we were not limited in terms of style to location. So we could have a truly international style. So we can put a building in Germany, in Sao Paulo, in Argentina, in the Mediterranean, wherever, the same building, same style building. So that's how the name International Style came about. And in 1949, Philip Johnson designs his glass house. Now, New Canaan, Connecticut is a cold climate in north of New York City, and hot summers. And this is a single glass box. And the idea was it's in nature and you become part of nature, but in essence, you kept nature out. You can only see nature through it, but you kept it out because now you can climate control the whole box. And it's even single glass and we can do it. There's that much between you and the exterior. But with abundant energy, you just pump it in and off we go. By the 50s, when I went to school, then we started building larger buildings, high-rise buildings, columns again all moved in. We had a curtain wall, we just hung thin single glass walls on all our buildings. We designed, Brasilia was one of the first entire cities that was designed and planned on those principles, the principles of modern art. Big wide boulevards, wide streets, housing blocks set back in a park so that they all got light. And it was really started to set out all the planning principles that we now see today. So that was in the 50s. And back then, this is Sao Paulo back then, you can see Sao Paulo built out. Does anybody see a curve in there? No. It's all rectangles, right? Why is it all rectangles? Because these were the tools we had back then to design buildings. When I went to school in the 50s and 60s, we had a T-square. You ever try to work with a T-square? First of all, put a T-square on the side, and it always moves. You can never get a straight line, really straight. And then that's the ink pen we had to use. You had to dip it in a bottle of ink, and there was a little wheel, and if you wanted a thick line, you'd open it up a little bit. If you wanted a thin line, you would, and then you'd run it along the side of the T-square, and the ink would then hit the T-square, get in under the T-square, and then you have a big blotch on your piece of paper. So then you have to wait till it dries. Then you had to get a razor and then scrape off all the ink. That's how buildings were designed and built and dimensioned back in that time. That's why there were no curves, because you had a French curve, which is this little thing down here, but there was no dimensions on it, and so you couldn't build it in 3 dimensions. So if you did a curve, it never happened. So you could do a half circle, because that you could dimension. So there were some half circles around. But the entire world was designed and built out using these tools. Then back in the late 60s, sort of middle 60s to late 60s, we got a parallel edge. So at least the damn thing we could actually draw a straight line. And they lifted it up off the paper so that the edge was lifted off so the ink didn't slide under. And then we had a rapidograph, which just let the ink out nicely, nice and easy. And so it was easier to do. But still, square buildings. Everything was rectangular. Then those were the tools. Then 1973 comes along. OPEC shuts off all the oil. Energy prices go through the roof. You couldn't get gasoline. Oil and gas natural gas prices went up. Coal prices, electricity went up. Everything went up. And Carter was the president back at that time, and he said, "We're getting off of oil." That's it. I remember he called us to the White House. There were a bunch of instructors. Remember, we got to get off of oil. We got to get off fossil fuels. And so that started this movement called the passive solar movement, or the solar movement. In 1975, now it's a little bit of history here, I started teaching at the University of New Mexico in the early 70s. I was a little too radical, so they kind of forced me out. And so I wanted to go teach at Berkeley. So I was a finalist because I had worked for Ed Barnes, I worked for big architects in New York and stuff. And I was a finalist, but I didn't get the job. So waiting in the hallway, Oregon and Berkeley at that time were like sister schools. They were both working on the pattern language and the Oregon experiment and everything else. The dean at Oregon was there, and I walked out. And so there were 3 finalists. So he picked up the other 2 people to come teach at Oregon, because Berkeley had done a major search, and everybody wanted to work at Berkeley at that time. So anyway, he offered me a job at Oregon and said, "What?" I said, "Well," I said, "Okay, yeah, I don't have a job, but what would I teach?" He said, "Solar energy." This is it's the early 70s, 72, 73. And I said, I don't know anything about solar energy. He said, "You live in New Mexico, right?" I said, "Yeah, I was teaching at University of New Mexico." He said, "We're in Oregon. There's no sun. You got to know more than we do. You're from New Mexico." So I said, "I'll tell you what, I'll make a deal with you. Give me 6 months, half a year, and I'll come the following semester. And I'll talk to people in New Mexico and figure out what this solar energy is all about." Okay, so I worked in New Mexico with a bunch of engineers, and after 6 months, I had designed actually a solar building for an engineer. He explained all the principles and everything else, and we worked for 6 months that way. And so I came to Oregon with a suitcase full of punch cards, right? This was the computer room. There were no individual computers. There was a computer center at Oregon at that time. And I came with a suitcase full of these punch cards. Now, each punch card is one action, computer action, like. So that is a program, all those punch cards, for one space, and you run it for one day. That's all you could do. And you had to take that suitcase to the computer room and give it to them, leave it overnight, and then the next morning you'd come back and you get a ream of paper with all these numbers on it and everything else. And that was one space facing whatever direction, whatever glass you had in it, for one location. And so for a year and a half, my graduate students and I ran this one space. We turned it this way, turned it that way, put it here, put it in New York, put it in Sao Paulo, put it all over the place, plastered our room about this size with this computer papers all over the place, looked for patterns and everything. And by the time we were done, we figured out how all the solar systems worked. But it was all, and we were panicked all the time that if the suitcase fell or the cards fell out of place, you would not know where they would go. Your whole program would be ruined. It'd be almost impossible to do it. So anyway, that's what it was like then. We did the entire passive solar energy book using that suitcase program. And then Ken wrote his book, and everybody was on the solar track. And there was a lot going on at that time. We had an architecture practice. We designed a conservatory, all-glass building with no heating or cooling system. We changed the properties of the glass, ran the program day and night to figure out the properties. We did the Mount Airy Library, it was all day lit. We reduced the energy consumption just through design because it was photovoltaics were too expensive. You couldn't buy them, they were a fortune. Even solar hot water you could do, but that was even expensive. So everything had to be done through design. So we wanted to see how much can we reduce the energy consumption of the building. We went to the White House, showed them what we were doing. They were like, huh, you got that? You went from, that's what the buildings were using, and you got your library to use only that amount of energy? So all that was happening. Lo and behold, in the 80s, middle 80s, the first computer came out, the first laptop, the first Mac. And Ronald Reagan came in, worked out a deal with the Saudis, turned open the spigot, dropped the price of oil down through the floor, so energy cost nothing again, and kind of the passive, all the work that was done at that time didn't go away, but it kind of, and it didn't go underground, it kind of went along by itself. And people kept working on, people who were working in it kept working on it. But not everybody else. Everybody else was then into back to form and space. And then computers got more sophisticated. Then we could finally draw a curve, actually make a construction document out of it, and get it built. And now things are very sophisticated. So this is what we're building now. We can actually design the most incredible buildings and spaces that you can ever think of. And we can actually get it drawn, get it dimensioned, and get it built. And you see it all over. Just incredible stuff. No more little rectangles all over. So that's where we are today. And in planning, we picked up the modern principles, planning principles of wide boulevards, wide streets, and it's still pervasive today. If you go to China, for example, that's just a street in China. China's just 6-lane streets, crisscrossing all over the place, not like New York, smaller streets. Turkey, the same thing. So modernism, from way back then, which was revolutionary, was essentially based on fossil fuels, and it persisted until today. Okay? Without fossil fuels, you can't do all that stuff. And modernism was a revolution, a real revolution. And it was based on principles that were utopian, and they actually took hold. And people actually lived better for quite a long period of time. So modernism was a paradigm shift. And it was a very radical shift at that time. Now, 2018. We need another revolution, because that revolution is really old now. And it's gotten us into, at the beginning, it got us out of a lot of problems, but now it's gotten us into some major, major issues and problems that have to be solved. So we need another paradigm shift now in architecture and planning, and it's beginning to happen. Now, what are the issues? By 2060, world population is expected to increase by 2.67 billion people. I want to put that in perspective. By 2060, world urban population is expected to increase by 2.75 billion people. That means all the growth that we're going to see in the world is going to happen in cities, in dense urban areas. To put it another way, every week, about 1.5 million people worldwide are moving into cities. Every week now. Cities are growing exponentially. Today, global building floor area, we know, is 223 billion square meters. So that's everything. That's this building, San Luis Obispo, the state of California, China, India, everywhere. That's how much square meters of building we have in the world today. Now, try to process this. By 2060, global building floor area will increase by 230 billion square meters, double the current worldwide building stock. So think about that. Everything you know today, in terms of area, building area, we're going to design and build new and add it to what we have. We're going to essentially design another planet and add it to the built planet that we have today. Now, we'll tear down some of that, about 1/3 of what we have now, but that's what we'll add. And you only have to go to China or some of these other countries to see that happen. We were in China recently. I was at a meeting in Shanghai, and they wanted me to come back next year. And I said, well, where's it going to be? It's a long flight, and I'm thinking. They said, well, it's going to be in Guangzhou. So I'm thinking, oh, Jesus, probably somewhere in the middle of the country. You know, it's going to be hard to get to. You know, I don't know if I want to go to Guangzhou. I said, I'll see. So I got back home. I opened up my computer. I typed in Guangzhou, China, to see what Guangzhou was like. Guangzhou is a city of 22 million people in China that was recently built out to that size. And every major architecture firm, architect, has signature buildings in Guangzhou. And when you go to Guangzhou, it's unbelievable. It's unbelievably beautiful. It's on the Pearl River, and it's all new. There's skyscrapers everywhere. It's amazing how much building is going on. And when you start to see that, you realize, yes, we will rebuild the world in 4 decades. And who's going to be responsible for all of that building? I'm looking at them right now. You're going to be responsible for all of this. So you have a huge opportunity that doesn't come along. You know, architects have been complaining forever that, well, you know, they think lawyers are always, you know, they think lawyers are better than us, and doctors, you know, their status, and our status is way down here. We've now moved up the food chain to right on top. If we don't solve the problem that we have now in the next, actually starting right now, but then moving out into this next 3 or 4 decades, it doesn't get done. It's really, the global problem that we're facing now with climate change is really at the doorstep of the architecture and planning community. If they don't solve it, it doesn't get done. It's impossible to do it. Only we can do it. Just like the modernists, that's where we are today. The world got together in 2015, in December 2015, and they laid out, the Eiffel Tower lit up that night, 1.5 degrees, and the world came together and signed an agreement. The first time the world, everyone, signed an agreement, except I think for 2 countries. And they said we have to keep global average temperature below 1.5 degrees Celsius above pre-industrial levels. Now, pre-industrial levels was pretty stable for hundreds of thousands of years. It went within a certain range, and that civilization started and all that. Now, it's gone out of that stable period, and it's rising. And the scientific community said 2 degrees C, we've got to be under 2 degrees C, preferably at 1.5. And if we do that, if we peak CO2 emissions between now and 2020, it's a year and a half from now, 2 years, and then get on the decline and phase out fossil fuels or fossil fuel CO2 emissions by 2050, that means no more oil, no more gas, no more burning it and putting CO2 in the atmosphere. Coal's on its way out already. But if we don't do that, we don't make it. So in order to stay under that 2 degrees C, we have to stabilize emissions now, roughly in the next few years, and then get on a steep path to phase out fossil fuels by 2050. If we do that, that's the green line down at the bottom. We go up to get close to 1.5, 2 degrees, the planet, and then it starts coming back when we phase out CO2. It starts coming back to pre-industrial levels, the climate we've always known. Now, scientists have told us and told me and told everybody that at 1 degree C, global average temperature rise, we will begin to see what the future is going to look like. We're right at 1.1 degrees C now. We've got another half a degree to go to stay under it and then come back. And you're starting to see what's going on. We're seeing flooding everywhere now. We're seeing fires all over the place. Places are getting hotter. We're beginning to see the effects of climate change now, and that is only going to get worse unless the architecture and planning community steps in and redoes how it thinks about design and planning and creates another revolution. Now, this is a scientist, Jeffrey West, who I know from Santa Fe, is at the Santa Fe Institute, wrote a book called Scale. It's a great book. You ought to see it, or at least look at this TED Talk on the internet. But anyway, we worked together very, very early on, and then he got involved in cities, and he developed a theory of cities, how cities grow. Because cities now are growing exponentially. So we're doubling population in cities like Guangzhou, 22 million people. It was a little farming community before that. We're doubling at much shorter periods. And in science, you cannot continue to grow exponentially without collapsing, because then you double and the time is so short, you have so many problems, you have a collapse. But so in studying cities, he sees that cities are growing exponentially. The problems build up. People are moving into cities because wages increase faster than population. Everybody wants to make more money. There are jobs available. There are more patents. There's more social interaction. There's all sorts of benefits to moving into cities, and that's why people are flocking to cities. That's why we have 1 million people moving to cities every week, 1.5 million people. But the negative stuff goes up faster. There's more crime, there's more pollution. It actually goes up faster along that exponential curve than population. So not only do the good things go up faster, but also the bad things go up faster. So how do cities then deal with these bad things? Well, they innovate. Cities attract the best people, the brightest people, a lot of energy, and they're great at innovating their way out of these problems. And so they're able to then innovate their way out of these problems and continue to grow. Then the problems catch up to them. There's more disease, there's more communicable disease. They figure out how to deal with that, and then they're able to grow again. So cities keep innovating. But what Jeffrey found, and this is every city he's studied all around the world, is that as you keep growing, the time for innovation, because you get further up the curve, the time for innovation shortens. So you're on kind of a treadmill. You innovate, and then, well, you go along for a while, then things pile up, you innovate again. Well, now they pile up a little faster because you're growing faster, then they got to innovate again. So I was in Shanghai, and this is like 5 years ago, and the congestion is unbelievable. The city's grown huge, and there are cars everywhere, and you get in a cab, an hour later, you've only gone 2 blocks. There's so much congestion. So 2 years ago, a year and a half after I come back to Shanghai, all of a sudden, there's not that many cars, but there are these bikes everywhere, all over the place, on the streets, mobikes. So they figured out that you didn't need stations for the bikes. You just needed to put a clamp on the back to activate it with your phone. And if there was a bike there and you wanted to take a ride, you just unlock it with your phone. The meter starts running, charges you 15 cents an hour or half hour. You go wherever you're going to go. You don't have to find the station. You get off the bike, you hit the button, the meter stops, the lock locks, and you leave the bike there. And somebody else picks it up. And all of a sudden, everybody's riding bikes in Shanghai, and traffic congestion is not as much anymore. So they figured out a way to deal with traffic congestion. Well, remember and Jeffrey West said you figure things out, but you condensed, you got to figure out, then you get more problems and stuff. Well, this is what happened with the bikes. All of a sudden, there's bikes everywhere. Everybody wants a bike. Everybody's riding on the bikes. And in the popular destination now, they're just dumping the bikes. You get off the bike, you just throw it up there, you lock it. Okay, so now they have to innovate again. Well, the time for innovation was a year, from going from congestion to the bikes to now a nightmare with the bikes. So now they have, all the bikes are on GPS. You get this kind of thing. You want 2 free rides? You go get a bike from this place and move it over to this other place. Somebody's going to get the bikes, and believe me, there'll be another problem 3 weeks from now, and they'll have to innovate their way out of that. So anyway, that's the way this thing is working. So I was talking to Jeffrey, and I was saying, Jeffrey, what about climate change? It's a different kind of animal. It's not like bikes, not like congestion. This is life and death kind of issues. So he said, I don't know. So I said, well, we'll work on it, and then let's get together and talk about it. So we took Houston. Houston just had a major flood, right? So I looked at Houston population growth, and I picked that off the internet. And you can see Houston starts out, but now it's an exponential curve. The population is doubling at a very short period of time. They're now at over 2 million people. So I plotted floods, because we just had a major flood. So Houston had a flood, so they have very good records. So I looked at major floods in Houston. Well, there was a major flood in Houston in the 30s, early 30s, 1930s. There was a major flood. So what did they do in Houston? Well, they built some reservoirs above Houston, 2 reservoirs, to hold back as the water came down so it didn't flow through the city, and then they could let it out coming through the city. That bought them 30 years, no floods, right? Then in 1960, 61, 62, they had a major flood. So they had to innovate again. So now they dug out the bayous that go through the city, dug them deeper, put sidewalls on so they could hold more water, so you didn't get any flooding. That bought them another 20 years, no flooding in Houston, right? Now, climate change starting to kick in the 60s, you see. This is what's happening in Houston now. There's a flood almost every year in Houston. So what's happening is warmer air going to hold more moisture, so when it rains faster and harder, and you get more rain in a very short period of time, so you get flooding. And that's happening more frequently now, and it's getting more difficult to innovate your way out of this. Now they're going to try it again. They'll try to innovate now to save the city and figure out how to get the water out to the ocean faster to do that. But climate change is now an issue, a big problem. And it's a planning problem, and it's an architecture problem. While Houston was flooding, we didn't know, but if you read the papers, all of Asia was flooding that same week that Houston flooded. We were so focused on Houston, thousands of people died in South and Southeast Asia and India. And so I took Chennai, which flooded and had a whole bunch of deaths, and I said, let me plot the major floods. They had actual records. And sure enough, you get the same thing happening with climate change. Climate change now is coming faster and faster if we don't get a handle on it, and is starting to create major problems in cities. And if we look at California, I was just in Hawaii, you see the same thing happening. This is global sea level rise, right? You can see for 60 years, sea level rise was happening, but at a fairly slow rate, and you can see that. Over the next 40 years, you see that red line. Now, the rate of sea level rise has picked up, has increased. And now, the last 20 years, you can see 20, 30 years that it's now rising even faster. If that gets steeper, sea level is going to encroach in low-level areas. All our cities are built along the coast, our major cities, New York, Boston, Miami. Those are in for a rough ride as that increases. So we need to get a handle on this. And we have the fires now in California. This study was just recently done, which shows the dryness of the forest in the western United States, and the acreage burned on the column to the left. And you can see in blue is 15 years, from 1994 to 1999, or 1995 to the year 2000. You can see the acreage burned. And then from 2000 to 2015, you can see the acreage burned, right? And the dryness of the forest. And you see it all moves up. And so you see with more frequency now, you're starting to see bigger fires, more acreage burned, and drier conditions because of temperature rise. So you're beginning to see the effects of all of this stuff that the scientists told us about at 1 degree. You're going to begin to see all this. We're starting to see it now, and the scientists are now plotting it and illustrating it to us. The good news is, I told you this was our problem. 75% of all human-produced global greenhouse gas emissions come from cities, from urban environments. And in those cities, who's producing all the emissions? Back in, 15, 20 years ago, we thought it was SUVs. Then we discovered, with the architecture stupid, it was us. This is, in cities, the percentage of emissions that comes just from buildings. In New York City, 71% of all the emissions in New York City comes from its buildings. In Boston, 73%. In Washington, D.C., 76%. In Beijing, 53%. Copenhagen, 76%. In Chicago, 71%. It's the buildings that are producing the emissions. And then, in planning, you can reduce the transportation emissions, which is usually a much smaller piece of the pie. So between the planners and the architects, we're responsible for all these emissions, and we're responsible for those graphs and the forest fires and everything else. It's at our doorstep. So who can fix the situation? We're going to have to do it. We're not going to, can't wait for government to do it. Can't wait for somebody else to do it. If we keep putting up what we put up, and we keep sucking up all that fossil fuels and pumping out CO2 in the atmosphere, we're going to be in big trouble. So we have an opportunity. We have become the most important professional community and building community on the planet. And why the U.S.? Why is the U.S. so important? Because everyone follows the U.S. I'm in China. What is California doing? We'll go to zero net carbon when California goes to zero net carbon. Everybody wants to follow California or New York in the world. Everybody wants to follow the U.S. At the summit in 2015, when the world signed on, no one signed on. For the whole week, that summit, the climate change summit went on for about a week and a half. The only countries that signed on were the small island states that are now trying to deal with sea level rise. There's like 50 of them. So 50 countries signed on to the agreement, but China no, US no, Russia no, EU yes, but that was about it in the West. The last day, we worked on the US contingent there, the State Department, and we said, look, it's the building sector, and we're doing it now. We had leveled out emissions in the building sector and leveled out energy consumption, which I'll show you in a minute, and we can reduce it. And we convinced them that the U.S. could meet the agreement to keep global average temperature below 1.5 degrees. We said we will get it done, and they agreed to it. And once they agreed to it, who else agreed to it? China agreed to it, India agreed to it, everybody else flooded in and agreed to it. And the 1.5 and the climate agreement was signed on the last day only because the US moved. And when I go to China, we got them to do a zero net carbon code. It's voluntary. When is it going to become mandatory? When we see California do it. We'll go. There's all sorts of MOUs between California, between the governments, between the labs and their governments and their labs. When the US moves, China will move. That's where all the construction's going on right now. So this community here in California has a huge responsibility. Now, I heard that Governor Cuomo in New York wants to beat out the new governor, and so he might actually announce a zero code, try to do that before California does. But there's a healthy, at least, rivalry growing. But we've got to get California to move. If California doesn't move, we're all in trouble. So we now need a revolution. We need to look at the built environment through a whole new set of glasses. We cannot keep doing what we're doing anymore. We need to act now. We need to make sure that every time we design something, it has an impact. And we need to scale it. That's why California is so important. If California does it, it scales to China. Believe me, California does something, China's going to do it. China doesn't wait. And in fact, when California does it, 2 weeks later, the whole country does it in China. It's amazing how fast they can move when they move. But they're always waiting to see what the U.S. is going to do. And the cities are not waiting for the federal governments, the national governments. They want to move now because they're the ones getting hit with climate change now. That's where the rubber meets the road. That's where the flooding happens. That's where everything happens. Everybody's moving into cities. The cities have to innovate. So 9,000 cities now signed up and said, we're going to get to zero by 2050. Now, they don't know how to get there yet. They don't have plans, but they signed up for it because they know they have to do that. So the work in the cities now is going to begin to happen and take root. So how do we do this? What's the magic formula? What do we have to do as designers and planners? Well, we need to obviously phase out all CO2 emissions by 2050, but we got to start now. So how do we get to carbon neutral in the built environment? That's where all the emissions are. It's a two-step process. Step one is design. It's what we do. We can get most of the way there, just like in the 70s. We got 80% of all the energy consumption and emissions, and we didn't know about emissions then, but we energy consumption we did because it was so expensive. We got 80% out just through design, just by how we oriented the building, the color we made it, where we put the fenestrations, natural ventilation, passive solar systems, you name it. All design. We didn't have photovoltaics there. We didn't have any of that stuff. But design, we can get 80% out. And then step two is the technology. Now we have the technologies. Then we didn't have the tech. Now you have photovoltaics. Photovoltaics are so cheap now. They passed the natural gas threshold. They were cheaper than all other fossil fuels, than oil and coal, and now they've gone past gas. So you can generate electricity cheaper with photovoltaics than you can with a gas plant. And that cost is moving down. It's not moving up. You don't see it moving up. Every year it keeps dropping. Wind energy just dropped 50% in the last few years, 3 years, I think, something like that. The cost of generating wind. Wind is now cheaper than solar even. So, design. We can get 70 to 80% of the way there. Minimum 50%, but 70 to 80% of the way there through design and planning issues. Transit-oriented development, so people are riding transit, bikes, walkable communities, so you actually walk, get a little bit of exercise, things like that. And all sorts of building strategies, everything from building form to glazing types, what you make the building out of, the color of the building, natural ventilation, all sorts of things you can do. Literally an unlimited palette of design strategies. And so once you get that down, then you add the technology, the renewables. Everything from site scale renewables to utility scale renewables to get to zero emissions. Once we get to zero emissions this way, once we start teaching this in the schools, but it's prevalent in the schools, not just a class, an ECS class, and not just that, design studio. Every project needs to be designed. Every single project you design needs to do three things, which I'll talk about in a minute. But once you start doing that, and then you go out in the world, you know what the architects, the big firms tell me? The CEOs of the big firms of Perkins and Will and HOK, they said when we hire young people, they change the culture of the firm. Us old guys, we don't change the culture of the firm. But when they come in, they want to do this, they want to do that, the entire firm changes. So it starts with education, and then when you go out, you change those firms. And they change forever. So, to help you a little bit, we put together the 2030 palette. This is years of research out of this area, out of Cal Poly, research from our friends in San Francisco, research from our friends in Oregon and Minnesota, people we worked with in the 70s. We took all of that stuff and everything new from the planners and put it into the 2030 palette. And it's all online. And it's all rules of thumb. So it gives you guidelines as to how to design essentially a zero carbon building or zero carbon community or zero carbon city. And it's in a very friendly format, and it's in plain English. There's no jargon. tells you exactly how to do it, and it gives you links to other sites that have information, so it's all there. And give you just an example, south glazing. You want to let this in colder climates. You want to let the sun in the winter. You want to keep the sun out in the summer. So you use sunlight to heat the building, keep it out in the summer so that you can cool the building. I'll give you an example. This is island wood up at 48, 49 degrees north latitude. So the rule of thumb is half the height of the opening in a horizontal projection above the glass, and you'll shade it all summer. Now, you'll never forget that. Half the height of the opening here in California, it's maybe, let's see, it's about a third probably. You're down here at 36 degrees north latitude, so it's about a third the height of the opening. You do that, you shaded the glass. That's all you have to do. This is not rocket science. We don't need a computer program to do this. And here you see that's the height of the opening is X. This is at 48 degrees north latitude. That's half X. There's the sun in the summertime. The glass is shaded. Those are the guidelines. But then you can fine tune it. Now we have all sorts of programs. Sapphira, Insight 360, programs out of California that'll help you then even massage it even further so that you can fine tune the design so you know exactly what's going to happen at any time of the year, any day, in any building, given any form. And you can look at daylighting and it'll give you graphics and everything's all out there. Not like we had it with the punch cards. We had to take it in and got a printout and all that kind of stuff. Now it's instant. There should be no problem designing to a zero carbon building. But we have one other problem that I need to bring up, and that is building materials. When we design a building, and if you're in a firm, you select every single material that goes into that building. Everything from the structure, is it a concrete building, is it a wood building, steel, what am I going to do it out of? To the flooring, to the lighting, to everything. You specify everything. Now we're going to build out the world in 30, 40 years, right? You know how much materials, concrete that is, and steel that is, and all that? I'm going to take you through a little exercise. This is from 2020 to 2050, so this is 30 years. This is the buildings that you guys will be designing and specifying all the materials. In year one, when you get out of school and you're designing something in the year 2020, year and a half from now, you design a building, almost all of the carbon associated with that building is in the materials, because the building is only operated for a year at the end of that year. If you design it, operates for a year, almost all of the carbon, 1 million metric tons of carbon, that blue line, that's how much carbon to make all those materials, concrete, that's it right there. And the building's only operated for a year, so only a little bit. Now, that's year one. So that's not all the buildings that exist now. The operations is big. I'm just talking about now the buildings you guys are going to be doing. So in year two, you're working for Skidmore or somebody, you design a building, you're on a design team, you design a building. Now you have the building you designed in year one, the building you designed in year two. That's the embodied carbon again, because you designed that building. Let's say it's the same square footage and everything. And now you have the building that you built in year one. It operated in year one, now it operated in year two, and you add the building from year two, that operations, and you get that orange bar gets a little higher, right? And in year three, again, you design a building. Now you take now you have the first building that was built 3 years ago has been operating for 3 years, and you add that to the building that's been operating for 2 years, and then the building that's only been operating for a year. Now the orange bar gets higher, right? So now I'm going to take you through, this is globally, or you doing one building at a time over the next 30 years. I'm going to take you all the way out. So this is just the buildings that you guys designed between 2020 and 2050, how much of those buildings, if you design a building every year, and every one of you design a building every year, and we add up all the buildings in the world, how much is embodied carbon and how much is operational carbon? So now we'll play it out. And voila, what you see is that of all the buildings, just those buildings built between 2020 and 2050, at the end of 2050, 48%, or roughly half, of all the emissions associated with those buildings is building operations, is the lighting, is the heating, is the cooling, is all that kind of stuff. If you design it to today's standards. Now, if we design it zero net carbon, that goes away. That whole thing goes away. But then we're left with 52%, the embodied carbon, if we keep building out of the same materials made the same way today. So, knowing this, all of a sudden, in the US and around the world, a movement, a groundswell has started to rise. There's now 350 members of the Embodied Carbon Network of experts all over the world that are now thinking and dealing with this issue of embodied carbon and want to help the architecture community in specifying materials that don't have any carbon associated with them in the manufacture and use of them. In fact, they're talking about materials that actually sequester carbon. So when they cure over time, they actually suck carbon cure and things like that. So this is a whole new field that's opened up, and a network has started. Architect 2030 is one of the founders of it, but it's grown like weeds. You wouldn't believe. Everybody now wants to get involved in thinking about this issue. So what's the embodied carbon? Right now, we have 12 years of looking at life cycle assessments of every single material. So we know all the carbon, where it comes from when you dig it up to you transport it to you make it and all that kind of stuff. We have all those numbers. For every material you can imagine, we know how much carbon is in it, and we know the cycle. But we haven't done anything with it. Now we have to do something with all that information. We need a prescriptive path. This is how you reduce carbon. And we need a performance path if you want to do trade-offs to get a low carbon building, and you got to use this material, but maybe I can use a different material. That is all now starting to happen this year. A few months ago, the first website donated, that was embodied carbon to major materials, concrete, steel, wooden insulation, a materials palette. Similar to the other palette, a design, now it's materials. And this is just informational now. So the information is now coming, and specifications and standards. There are these 350, 400 people all around the world now working on specifications on how to get these materials lower carbon. And some of the big names in the industry, Microsoft and Skanska, got together to develop a low carbon calculator. So you can calculate every material in a building, and it'll pop out what the carbon content is of all those materials and give you options on what to substitute to get lower carbon. So all that is now beginning to happen. This will be available next year in 2019. It's called EC3. Okay, so to finish up, what has to happen in academia? What do you have to be doing and thinking about it? Well, every project in Design Studio needs to engage the environment in a way that addresses climate change. You cannot not think about this in every project you do. It has to be part of what you do. And it has to do three things. One is you need to dramatically reduce or eliminate the need for fossil fuels. So in your studio, design a building. How are you gonna design it so it doesn't use fossil fuels to operate? That's part of the problem. Now, we don't eliminate any of the other issues. If you're doing housing, you got to house people. If whatever building type you're doing, it has to work. It has to stand up. It has to do all those other things. But this must be a requirement. Otherwise, we're not going to make it. The second thing is you have to project out 20, 30 years, and those projections are available. Every city now has it. Every state has it. They know what's coming down the line because there's going to be some climate change built in. Even if we make the 1.52, there's still, it's going to grow for a while, and then it's going to come back. So we know what the projections are. So you have to design for that. Otherwise, you're putting people at risk. So you have to project for it and design for it in studio, every project. And then third, after a disaster, you've seen what happened in Puerto Rico, people without electricity for months, natural gas. In one place, natural gas took a year to get the gas back on. People living without, and these are essentials. So your building has to be able to respond. It can't, like, all of a sudden you lose electricity, there's no light, no daylight, you can't find anything in that, you know. So everything needs to be daylit. It needs to respond slowly to climate change and things like that so that you could still occupy these buildings. So they need to be resilient and need to be able to respond quickly when natural disasters hit. Those are the three things that need to be taught in academia now. So I'm going to leave you with this last hopeful, this is why I'm so optimistic. This is Seattle, Chicago, Los Angeles, and Atlanta, right? On the vertical column is thousands of BTUs, a square foot a year. So this is how much energy falls on a square foot of surface in a year in those locations. That's cloudy days, sunny days. It's averaged up over an entire year, okay? In brown is the roof, in yellow is the south facade. Okay, this is what falls on the roof, a square foot of roof in Seattle, in Chicago, in Los Angeles, and Atlanta. You can see LA is a sunnier climate, a little further south, gets a lot of sunlight, captures a lot of sunlight. So that's a square foot. Now, that energy is delivered to a building, to a square foot of flat surface in a year, free of charge. We're going to deliver that to every square foot of roof in those 4 locations, free. We don't have to dig anything up, we don't have to burn it, we don't need lines, power lines, we don't need anything. Just going to deliver it to you. And then we're going to deliver it to you on a square foot of south facade, 1 square foot, that amount of energy over a year is going to hit that facade. Clouds, everything, okay? So that's how much energy in Seattle, okay. Now, how much energy does a building use in a year, a square foot of building? Well, this is an average building. These are old buildings. This is not built to code yet. An average building uses 42,000, residential 42,700 BTUs a square foot a year, commercial institutional about 85,000, right? So that's how much a square foot. So these are 1-story buildings. So if they were 2-story, it'd be double that. But that's how much energy a typical building built in the year 2000, 1990, 1980, uses. Okay. Now, if we built those buildings to today's standards, we're down about 50%. Okay. So in the bright red bar, that's how much energy, if you build a code today, to Title 24, California, roughly that's how much energy a building uses. Now I'm going to give you all a problem. Okay, I gave you the problem to draw. You couldn't do it, but this one you can do. I'm going to take Seattle. This is, when they asked me to come to Oregon, this is how much sunlight we got there, right? This is how much energy falls on 2 surfaces of a building in Seattle, the cloudiest place in the U.S. Worst conditions. That's how much energy a residential and a commercial building needs per square foot in the U.S., in Seattle. Probably less in Seattle, it's a milder climate, but that's roughly what it's going to use. Now, That's how much you get free, delivered free. That's how much you need. Tell me you can't solve this problem? I asked this of a group of scientists in Pittsburgh. We had a whole room full of scientists, about 1,000 scientists. And climate change, there was this talk, I don't know how we're going to deal with this, how we're going to get this, and all this kind of stuff. So I said, I'll give you a problem. I gave him a problem. I said, okay, now, scientists, raise your hand if you cannot solve this problem, right? And they all laughed. Obviously, we could solve the problem. This is not rocket science anymore. In fact, we sent 20, 30 years ago, we sent Cassini to, to look at the rings of Saturn. We actually found 2 new moons. That's when we had the little Macintosh, right? We sent a probe there. Not only that, last year we killed the probe. We actually flew it through the ring, between the rings and the planet. There's an empty space there, right? We actually guided it right through that space so that there was nothing there, and then had it go right into the atmosphere of the planet and burn up and everything. That started 30 years ago, 20, 30 years ago, right? And that's the problem we have now, to save the planet? This is a joke. And we can't do it? Of course we can do it. But not everybody can do it. Only the architecture and planning community can do it. Remember that. So, this is your world. This is the world you're moving into. You will change the culture of all the firms that you go work for. You need to know how to do this by the time you get out of school, so that as soon as you get into the firm, you hit the ground running and you make those changes happen. Thank you. Yeah, you got to speak up then if it doesn't work.
I think you're punk rock for sticking with classic design before it was cool. But one question I have is, where does the percentage come from? Buildings are 50% of the
total, yeah.
Yeah, because I look at other organizations like the UN, and it's a lot smaller. So I'm wondering what.
Well,
your
50%
terms are.
is U.S. And the UN numbers. Okay, so when we started this back in 2002, we discovered the building sector, right? In 2002, there was no building sector. All the statistics that were put out by the government was transportation, industry, electricity, and then the only building stuff was on-site was actually the natural gas that you used on-site. Okay, not electricity. So those are the 4 numbers. So the building sector, residential and commercial, were these little slivers, about 1% or 2%, something like that. Then electricity was huge, and then you had transportation and everything else. So there was no building sector, and yet industry. So we were sitting in my office, and this is architecture practice. So we didn't know anything about climate change or anything like that. And the young people in the office said, Ed, you did all this work with all your friends in the 70s and 80s, and you come over and you give us critiques and you tell us, no, turn the building this way, put some glass here, shade it here, do this. We don't even know why we're doing this. So we want a seminar. We want you on Fridays. Every Friday, we want to break at noon, bring in the pizza all afternoon, and we want you to give us a seminar on what you did, all that research you did back in the 70s for the Pastor Solar Energy book. All right, so we started that. One day, somebody burned down an SUV dealership in Denver because SUVs were the poster child of climate change. Everybody thought SUVs, we got to get rid of SUVs. So the environmental activists were burning down SUV dealerships, right? They had just burnt down one not too far from where we are in Santa Fe up north. So one of the people who works, one of the young people said, why are they burning down dealerships? Do we have anything to do with this? So I said, well, I don't know. Let's look into it. So that weekend I was going to Disneyland, taking my granddaughter to Disneyland in California. And I took a book that I used back in the 70s to teach at the University of New Mexico called Limits to Growth. And I took all the books that I had, and I got there, and I opened up the Limits to Growth, and there's this curve, exponential growth curve of population, right? And it was the year 2000. That was a book I used in 1970. And it said, if we keep doing what we're doing now, we will double population from the beginning of time, of recorded time, the time Lucy or whoever was the first one stood up on its hind legs, to 1970, we hit, I don't know, 3 billion people, something like that. And because of exponential growth, we will double that in 30 years, in the year 2000, right? The book was written in 70. And it was 2000, and I was in Disneyland, and I had a computer, and I got on the computer, and sure enough, we were at 6 billion people. In 30 years, we did what took us from the beginning of time to 1970 to do. We did that in 30 years. That's like building the planet out again in 4 decades, right? So I'm going, holy mackerel. They hit it right on the nose. I mean, right on the nose. So I flipped the pages. There's another exponential curve. And it says in the Limits to Growth, if we keep putting CO2 in the atmosphere at the same rate, in the year 2000, we'll be at 3 point, I can't remember what the number was. So I got on the internet and I looked, and sure enough, we hit that number of CO2 in the atmosphere. And they projected in that book that all sorts of hell's going to break loose. We keep putting, because it's a greenhouse gas. And the planet's going to heat up and everything else. They didn't know how much and all that kind of stuff. They weren't as sophisticated then as they were now. And I went, holy mackerel. And so I tried to find the building sector emissions, and there was no building sector emissions. So I took the numbers and redid them. I looked at how much electricity went to buildings, and I carved that out of the electricity sector. I looked at how much how many industrial buildings there were that were heated and cooled and stuff, and I carved that out and put that in the building sector. I put in the little slivers for gas. And then I carved out, a guy named Richard Stein did a book, I can't remember the name, something in energy. Anyway, he had embodied carbon numbers. And I kind of extrapolated that and said, okay, this part of the industrial sector, I'll call embodied carbon, and I'll put that in there. And lo and behold, I came up with 50%. So I came back from Disneyland, and I said, we're responsible for 50% of this. And they went, in the US, this is the US now, and they went, holy mackerel. So they said, we have to write an article about that. So I said, okay, I know the solar guys, Solar Today, we'll write it. You know, it's the architecture, stupid, right? That's where we wrote that. But they said, yeah, you can write that, but nobody, you know, only the solar people are going to read that. That's all your buddies. They said, we need all the kids to read it. They said, you got to get it in a magazine like Metropolis magazine. I said, I don't know anybody in Metropolis magazine. He said, all the kids read it. This is back then. So I said, okay. So I called up Metropolis. I said, and the guy's New Yorker. He's like, what do you want? You know, and I go, I got some information here for you. We want to write an article on the building sector. He said, what do you mean an article? So I figure I'm from New York, so I know how to talk to him. So I said, hey, who's responsible for most of the energy consumption in the U.S.? So already now I know he's thinking. That's easy. I said, who? It's the internal combustion engine. I said, no, it's the building sector. He said, no, you're kidding me. No, it's not the building sector. It's impossible. I said, I'll send you the data. He said, okay, I don't have any time for this, but send me the data. I'll give it to some of the people here, and they can run it down. I said, okay. So I sent him the data and stuff. 2 weeks later, I get a call back. It's Martin Peterson. Hello, Ed. Yeah, it's Martin Peterson. This is now a nice, friendly attitude, right? Hey, Martin, how you doing? He said, the data checks out. He said, your data checks out. He said, we want to write an article. I said, great. I'm just writing an article for Solar Today. I want to write the article for Metropolis. He said, no, you don't understand. You don't write articles for us. We write our own articles. And I said, well, I'm going to do Solar Today. No article. You don't get the data. You don't get anything. Goodbye, Martin. Hang up. Next day, I get a call. Hey, Ed. Who's this? That's Martin Peterson. Hey, Martin, how you doing? You know that article? He said, look, we can't let you write an article. It's not how we do things. But I'll send a writer out, our best writer, to New Mexico. He'll sit with you. You tell him everything you have, show him everything. He'll stay there however long you want, and he'll write the article. Professional writer and everything. So I'm thinking fast now. And, New York, you're bartering, right? So I said, that sounds interesting, Martin. I'll tell you what. We'll do that, but I want the cover of the magazine. So he says, Ed, I can't give you the cover. The covers are done months in advance. We have covers done months in advance. The magazines are set up. They have a theme and all that. I can't do it. Well, Martin, no cover, no article. Sorry, goodbye. Boom, hang up. Next day, phone rings. Martin Peterson. Hey, Ed, how you doing? Okay, I can give you the cover. The October issue. I said, Martin, it's 5 months from now. I said, the solar magazine's going to come out earlier than that. I already did it's the architecture stupid. He said, we don't care. It's a different audience. I'll give you the cover if you let us come out and write. So I said, okay. So October of that year, 2003, the cover is 3 rolls of tracing paper, right? Construction documents with scribbled smoke coming out the top like smokestacks. And I plastered on the covers, architects pollute. So Martin and I are getting calls from every architecture firm in the country after that. How can you do this to us? What are you doing? We design places, for people to live and better. And I said, architects pollute. We kept pounding it into them. Within 6 months, they got on the bandwagon. We're going to solve this problem. So all the major firms now have signed on to the 2030 challenge and are really working hard to address this issue. And so the architecture community has really galvanized around this issue. Now, who's lagging? Well, maybe not Cal Poly San Luis Obispo, but most of the schools are lagging. And so the kids coming out, going into the firms, have to go through a whole learning curve to pick up all this stuff. That's why academia is so important now, because again, they change the culture of the firm, and they're not changing the culture of the firm fast enough. So we need more Cal Polys. I know you guys are all up on this because I know you're instructors. But in the rest of, out there in the rest of the US, it's not happening as fast as it needs to happen. But we're working on changing that. We have we planted some people in the NAAB, some friends who we'll see some big changes happen pretty soon. But anyway, that's how the 50%, so you asked me the 50%. You see, you got me off on a tangent here with the 50%. But that's how we discovered the 50%. Somebody in the office asked the question, what the hell are we responsible for? They're burning down dealerships. Do we need to burn down more dealerships? Let's get rid of all the SUVs on the road, And so we figured out SUVs were actually a small percentage of the transportation sector. Transportation sector was like 25, 28%, and SUVs were like 2 or 3% of that or something like that. And here the architecture sector was 50%. Now, worldwide, you see 37%, 39%, you see those numbers. Those are just building operations worldwide. And doesn't include all of the industrial sector or any industrial buildings or anything like that, or materials or anything. You start to add that in and it's big. So that's what that number is when you see globally the 37, 39%. Any other questions? Yep, we got one here. And then one here and then one there. And then we'll end it. We'll take 2 questions.
Yeah, yeah.
Hello.
Hey,
So I was just wondering if you could comment on Californian housing policy with regard to our new energy standards. You mentioned that the world follows California because we're innovative,
okay, yeah.
but and you have this chart right here. It doesn't seem like a very hard problem to solve,
It's
and
not.
it seems like we've had this solution for years. So I think maybe there's another issue is that our hands are tied. And as new upcoming professionals, I was wondering if you had any advice that you could give us
Yes.
with this political fabric that
Yeah.
we're not really familiar with.
2 things. One is your hands are not tied. That's the first thing. You can design a zero net carbon building. The problem is semantics. What happened was USGBC and everybody else got into talking about zero net energy buildings, okay? What is a zero net energy building? What's the definition? It's you produce enough energy on site to offset any fossil fuels you bring in. So if you're using natural gas, you're offsetting it with electricity you generate on site and that you put back into the grid. Or you generate enough energy for your building. Let's say it's an all electric building. You put it into the grid, and even though the grid could be dirty and you're pulling off, net you're using only renewables, okay? So you have to produce as much on-site as the building uses, even though you feed it into the grid and pull off energy that has a little bit of coal, a little bit, it's a mixture of all sorts of things. So that's zero net energy. Everything has to be done on site, right? So now look at the statistic I put up. 1 million people moving into cities every week, 1.5 million, whatever it is. And all the construction is going to happen in cities, and cities are dense, and you can't do everything on site. You got a 50-story building, you got a little teeny roof in terms of the floor plate, right? Maybe you can catch it on the south wall, but if it's dense, it's shaded and all sorts of things. So you need off-site. So you need to design an efficient building that uses a certain amount of energy, like 50%, 70% less than a typical building. You do that through design. And then the rest, you do what you can on site and then procure the rest, buy renewables. So you then set up a whole system of predictable purchasing of renewables so a city can then supply that, okay? So by going from zero net energy to zero net carbon and allowing you to go off site for some of the energy, clean energy, to import, because you can't do it in dense urban areas all on site, you then open up the possibilities for everybody to design zero net carbon buildings. So 6 months ago, we called Charles Ely here in California, who's a code guru, been doing codes forever, and I know Charles from the 70s and 80s during the solar movement. And he just wrote a book on codes and stuff, and we did the cover, and we did a little blurb on the cover. And I called Charles and I said, Charles, we need a zero net carbon code. We need a zero code. How long would it take you to do a zero code? He goes, I don't know, Ed. I said, let me think about it. I'll call you back. So hang up. 2 weeks later, hey, Ed, it's Charles Ely. Hey, Charles. It took me 3 months. I said, what? 3 months, we do a zero net carbon code. I can do a zero net. I said, how are you going to do that in 3 months? He said, I'm just going to use the regular code. And then we do the on-site and the off-site. We'll add it to the code. The code gets us way down anyway now. We don't need to reinvent a new code. Let's just use ASHRAE 90.1 2016 or the 2019 when it comes out, or Title 24, right? We just use Title 24. It's a really good code, it's efficient. And then we'll do an on-site calculator that'll tell you how much you can get on site. And then the rest you have to buy. And you have to buy it. You have to buy it. You have to buy clean energy, and it has to be newly produced clean energy above and beyond any, RPS or portfolio standard, whatever. It has to be brand new, attached to that building forever. 3 months you can do it? Yeah. Okay, let me call the California Energy Commission. California Energy Commission, you having a summit? Yeah, we're having a summit. We're going to design a national and international zero code. And California's not going to have one because you have Title 24, and the zero code uses ASHRAE, and Title 24 is its own beast. Uses time-dependent value. It's like a nightmare to figure out and all that kind of stuff. So I said, we'll do one for you if you send me a letter saying you want us to do a zero net carbon code. So the governor's office sends me a letter, the California Energy Commission sends me a letter. We have Charles do a zero code, so now we have a zero code international and national standard using ASHRAE, and we have a zero code for California at zero-code.org is the zero code. Now, I'm supposed to give the keynote at Buildings Day the day before the summit here in San Francisco, and I'm supposed to give the keynote for a whole day of building sector people coming and doing all this stuff. So I'm putting together the keynote, and all of a sudden I figure out 2030, Architecture 2030, we're way too late. 2020 is the date. We've got to get this thing, we've got to get a zero code in by 2020. We cannot wait. Call up the governor's office. I say, we need Jerry Brown to sign an executive order that California is going to go to a zero code by 2020, zero net carbon code. We got it all designed for you. We raised all the money and did it. California didn't have to do anything. But we need Governor Brown to do it. They wouldn't do it. So now we're waiting for the new governor to come in January, and we have a whole group of people that are going to go up to Sacramento. We're going to meet with SMUD and a bunch of utilities, and we're going to get a meeting with the governor, and we're going to tell him he's got to do an executive order or something to get that California zero code mandatory. Latest 2022, but 2020 we want it mandatory. Now, tomorrow we have a meeting with San Luis. California Energy Commission has told us, get some cities to adopt it right now. It'll be easy for me to then do it, right? We can then mandate it if you start getting a wave here going. So we met with Palo Alto. They already did their study. They want to adopt the zero code. We met with San Francisco. We're talking. We'll meet with San Luis. We're going to start meeting with a bunch of people. All of a sudden, we got a call from Oregon. Oregon wants to adopt the zero code. City of Portland wants to adopt the zero code. All of a sudden, we got a call from the governor's office in New York State, from Cuomo's office. This is just the past few weeks. This is just the past few weeks. So from Cuomo's office, we get a call, right? Ed, yeah. Has California adopted the zero code yet? No. We don't know when, but we're pushing them. You mean Cuomo can announce, he's got to make a big announcement in January, adopting the zero code. He'd be the first in the world to adopt the zero code? I said, yep. If he does it, yep. So we have scheduled a presentation to the state of New York next week to show them what the zero code's all about, to try to convince them to get Cuomo to do it before California does it, so that New York does it. So anyway, that's how the game is played, and that's how it works. But we've got to get California to do it. And the reason is that Lawrence Berkeley Lab, PNNL, but especially Lawrence Berkeley, the state of California, they have all these MOUs with all the organizations in China. I didn't show you this, but I could have. The lecture would have gone on for 2 days here. But if you look at where all the construction is going to happen in the next 10 years, most of it, the biggest chunk is in China, then India, and then Latin America, the US, every place else. But that's where, Southeast Asia, that's where most of the construction is happening. That's why California is so important, because they have the connections in with China. And every time we go to China and we talk to them about zero net carbon, we get them to move, they always want to move. They always want to do things. They do things very quickly. But they won't go the extra mile until California goes. So that's why California is so important. Okay, we had one more question.
Hi, so I'm part of the mechanical engineering department, student, HVAC student. So I have two questions for you. One, how can our engineering department and the HVAC industry support the architects in this mission? And two, how do you see Architecture 2030 and goals like this fitting into the existing building and retrofit part?
Yeah, that's a good question, and we could have gotten, that's another whole lecture. But the engineers are really important. We have to electrify. What you're going to see in California now is a whole movement to electrify, because you got to get off of gas. Because once you lock in gas, it's locked in for a long time. You build that infrastructure, and now you have, you know, and we've been going from coal to gas to get the quick reduction, and then we lock in gas, and it's a nightmare. So there's a huge movement now in California. It's kind of underground, but I think it's going to bubble up any minute, because I'm getting 1,000 emails of electrifying. And Santa Rosa, I think, will be the first town or city to say no hookups, no more hookups for residential. Can't hook up if you're going to build a residential building. So they're going to try to electrify, because the state of California has they have a way to get the grid all the way down to zero emissions by 2050. At least that's what they want to do. But now, if the new buildings overwhelm, if they're not designed really efficiently, which is why the zero code is so important, then they won't be able to do it. But we think California, they're on the right path now. So if they electrify, the only way you're going to phase out emissions is by getting rid of natural gas. And the only way to do that by not allowing it anymore. And then when buildings are renovated and stuff, you incentivize them to go to electric. So that's how so mechanical systems, heat pumps, that's all going to happen. And architects are going to have to work with engineers to figure all that out. And the second part was, what about the existing building stock? Well, what I could show you is that we did a study of Seattle. And if you go on the internet, on Google, and you type an aerial view of Seattle, right, or aerial view of San Francisco, or aerial view, you step way back so that you get an aerial view of the whole city, you will see a clump of all these high-rise buildings, and then thousands, hundreds of thousands of small buildings. The clump of high-rise buildings is roughly equal in square footage, or a little bit less, than the miles and miles of the small buildings, and hundreds of thousands. So in Seattle, there are, 8,000 big buildings over 20,000 square feet, and then 190,000 or whatever the number is. We have all these numbers of small buildings. So that's 190,000 building owners of the small buildings, but only 5,000 building owners of these big buildings. And if you look at how much emissions are associated with 5,000 building owners, it's half of all the emissions in the city, and then hundreds of thousands of the other half. So we looked at New York City. The cutoff in New York City is 50,000. Lower Manhattan, Midtown and Upper Manhattan, downtown Brooklyn, that's where all the big buildings are over 50,000. And then Queens and Staten Island and miles of small buildings. There's 1 million small buildings under 50,000 square feet in New York, and 23,000, teeny number, of big buildings. So we said, well, let's look at Long Beach. Long Beach, there's 1,400 big buildings, over 10,000 square feet, and then 190,000 teeny buildings, right? Every city we've looked at has a cutoff with big buildings responsible for 50%, and then zillions of small buildings responsible for the other. Okay. I can make a policy for that small number of buildings and building owners that politically I only have to deal with a very small number, so it's politically easier. They'll come screaming and stuff, but they have money, the big buildings, all that. And I can say by date certain, by 2030, you have to reduce your energy consumption or emissions by 50%. And I give them 12 years to do it. And I give them incentives to do it early. But if they miss that date, whoever owns the building misses that date, it's a huge penalty, fine. Okay, that gives them a long time. What we found out is when a building undergoes a capital improvement cycle, it costs 75% less to do the efficiency upgrade when they're actually breaking the building open, doing construction, renovating and stuff. To do the efficiency upgrade costs nothing. But if you try to get them to do it when they're not doing it, the startup costs and engineering and architecture fees and all that kind of stuff, it's a fortune. So you give them a long period of time when they're going to hit a capital improvement cycle to do the upgrade. Otherwise, 10 years down the line, they get a fine. Okay, now you don't have anybody screaming, you gave them enough time, all that stuff. And you let them buy a percentage off-site that lessens the burden. But now you have a market for renewables. Well, what about 1 million small buildings in New York? How are you going to get at those buildings without 1 million people coming down to City Hall with signs and everything? You're making me do this. Well, you got to find an intervention point. When is that building going to undergo construction? That's when you want to get them to upgrade. Well, when do buildings undergo construction? When they change hands. When somebody buys a building. I'm going to redo the kitchen, I'm going to redo the floors, I'm going to put insulation in the attic, I'm going to change these windows, there's rotting over here, I'm going to do this. 23,000 buildings change hands. They're all small buildings in New York every year. If you add that all up, by 2050, every building's going to change hands. So now you have another policy that says when a building is sold, within 2 years after that building is sold, you have to upgrade it to a certain standard. That's how you get at the building stock in the US. You have a two-policy system, one for the big buildings, that's date certain, and the other at an intervention point when it undergoes an upgrade. In California, when it has to do a seismic upgrade, when you do that and you open the building up, you do the efficiency portion at that time. You mandate it. So you do it at a time when it's not burdensome and it's cost effective and the payback is really quick, and you have incentives for people to do it, and you have financing programs for people who are marginal so that they don't get hit hard and they're able to do it and they realize the savings. You do that, it's politically viable. We're now working with 12 cities around the country to develop these policies. San Francisco's one. Let's see, in California, San Francisco, Palo Alto are the only two we have in California, but Seattle, Portland, Phoenix, New York, Boston, Minneapolis, Grand Rapids, a bunch of cities we're working with to help them develop these policies. And the way we came about this was, we said, okay, let's first get the data on the cities, and then just like we did the past solar energy, we put up reams of paper. What are the similarities? Jesus, they all have these big buildings. There's a cutoff, and they're responsible for 50%. So we do the 50%. Where's that cutoff? In New York, it's 50,000 square feet. In Long Beach, it's 10,000 square feet. Here, it's probably 15,000 square feet. You probably find something like that in Cambridge. All of the big buildings are at the universities. And then the rest is, so you get the universities. Now you only have a handful of universities. You make them do it. That's it. You're a university. But you're not going to do it? You know what the PR is going to be if you don't do it? The negative PR? You can get them to do it in a heartbeat. So you just have to be smart about how you go about doing it. But you have to get the data. And if you don't have the data, then you're flying blind and trying to develop policy, which is what all the cities were doing.
All right,
All right.
Ed Mazria, thank you for your work and for giving us a problem we can solve. Thank you very much.
Solve that problem.